Good morning, everyone, and welcome to episode 5 of the Informs Service Science online forum. In this episode, we are going to explore management analytics and the digital twins. I'm Guangwen Kong, Associate Professor at Temple University, and I will be your moderator today. First, it's my pleasure to introduce our speaker, Professor Opher Baron. He is the University of Toronto Distinguished Professor of Operations Management at the Rotman School of Management and holds a PhD from MIT Sloan. His research spans queuing, business analytics, service operations, especially healthcare, autonomous vehicles, and supply chain management, with publications in leading journals such as Operations Research and AMSA. He's an active community leader, serving on advisory and editorial boards, and delivering numerous invited keynotes. During the pandemic, he helped launch COVIDPPEhelp.ca, which routed millions of PPE items. In 2024, he co-founded SimulQ, where he is the CEO. SimulQ is a company that builds data-driven digital twin simulators from event logs using machine learning and queuing theory. Now, please join me to welcoming Professor Opher Baron.
I just want to make sure that everybody see my screen.
Yes.
That sounds good. Okay, so I want to thank you all for coming. It's a pleasure talking here today and share with you a little bit of my thoughts on how analytics and AI are changing the future, specifically in the context of operations, more specifically in the context of operations of congested systems or queuing systems, which are abandoned in services. So I'm going to talk a lot about queuing and waiting time today in the context. My prime example is going to be emergency department, and we'll talk a little bit about that. So first of all, I want to show you how I think about management analytics and how it works. So that you see those kind of two axes here. The y-axis is the past and the future. Oh, it started raining here. And the x-axis is essentially existing systems or alternative systems. And we only have data on real systems in the past. That's the only place where we have the data in this kind of context. And when we analyze this data, it's a little bit like studying history. Descriptive analytics basically tells us, hey, we look at the data, we describe what happened, we try to understand things, try to understand what impacts what, and so on. And those are kind of things that are, it's really nice because it gives you an understanding, but that is not what we do in terms of taking decisions. So in order to take decisions, there are a couple of additional things that you need to do, and you want to do them in a data-driven fashion. So the first thing you're going to do is you're going to have some descriptive analytics, and you're going to do some predictive analytics on top of it. So this is a standard regression kind of question. Last week, on Monday, there were 80 people coming to the emergency department. The week before, there were 75. How many people are going to come to the emergency department next week on Monday? About 77, 78 with some standard deviation. You know, if it's a snowy day, there may be a little bit more people coming. If it's a heavily snowy day, not too many people are coming because they cannot drive. So you have this kind of ability to predict what would happen, what would be the length of stay in the emergency department, as an example. So this is really interesting, but the problem with it in terms of, again, thinking of decision and management analytics is that it only focuses on the existing system. So what we want to be able to do when we want to manage things, we want to change the system. We want to go into an alternative system that doesn't necessarily exist. So in order to do this, you need to do what I call comparative analytics or inference. You can think about the questions kind of how long will a customer wait in the emergency department if I change my policies, right? Say that I change the shifts of the doctors, and rather than starting at 8 a.m., 4 p.m., and midnight, I move them to start at 6 a.m., 4 p.m., and midnight, right? How will this change the system? And to do comparative analytics based on data, it's really, really tough. Both the 2011 and 2021 Nobel Peace Prize in Econ went essentially to try to take this step of establishing the causality in order to have the right analysis as you do comparative analysis. And comparative analysis also is, as you see, works both in the past and in the future. So in the past, it's counterfactuals. What would have happened yesterday if the nurse didn't have a flat tire and would show on time, right? So that's a counterfactual question. Some counterfactual we do by benchmarking, data envelopment analysis or stuff like that. But when you want to go to different systems, you need to be able to do this while understanding the causal structure of the system. What impacts what? If snow creates more arrivals or less arrivals, right? If a doctor coming an hour earlier helps to reduce the backlog in specific times such that overall the average length of stay is going down. Those are things that you need to understand the causality in them. And this is why it is so complicated to do it with data. And doing it just with a predictive analytic model that doesn't consider the fact that you change the system is simply wrong. This is not a matter of going out of data. This is a matter of going out of model. When you change your model, when you change your system, you need to change how you predict what would happen in this system. Right? So, just changing my X1, the number of people in the system, the number of servers in the system from 1 to 2, that may not be sufficient to capture the fact that you add another server. So you need to understand what other impacts those changes have, and this is why it is critical. Now, for us, the trick is that this is insufficient. Again, it's nice to be able to describe and compare different systems, but what we want to be able to do is to do prescriptive analytics. So, and this is to me the hallmark of management analytics. You come, you take the data, you understand what's going on, and you provide a recommendation to get not just an alternative system, but a better system. Right? This is operations research, operations management. We are trying to improve the management of these service systems, and we're trying to prescribe some good process change that will improve the system. So just wanted to see if anybody have any questions on this, or if this makes sense. If you have questions, just unmute yourself and ask, please, guys. All right. So this is kind of the way I'm thinking on management analytics. Let's get conceptual model 1. I'm going to take you now to conceptual model 2, which goes a little bit more into how I see this plays a role in the context of making decisions in organizations. In the context specifically of queuing systems here, but the ideas are broader than that. So I'm talking about the digital twin processes. So what is the idea of the digital twin processes? Broadly speaking, the idea is that you create a model of the system, you act upon this model, and that there's a interaction between your model and the system. So it's not just a model that is completely isolated from the system. There is interaction between them, and they feed each other. So how can we do that in the context of management analytics? You start with the data that you have in the system. Think about your ERP system, where you have data on what happens in your organization, in your process. In healthcare, these systems are often Epic or Cerner or Meditech. So you have data on what happens in the hospital in those systems. In the context of queuing, the critical things for me is what I define event log. And in this event log, there are three important parts. Part one is a patient identifier, or more generally, a job identifier. Part two is the activity, what happens, what processing has happened to this job. And part three is the timestamp of when it happens. So for us, as thinking about queuing and management of a queuing in the context of service system, those are the three essential things for us to be able to look at the queuing systems. I need to know the customer, I need to know what happened, and I need to know when it happened. Obviously, you want to add on top of it many other things that may be useful in the context of supporting features, say for machine learning model. You can think about age, gender, the acuity level, and so on. But those are the three critical things. Without them, we cannot do any queuing analysis. Once you get these three critical things of the event log that describe the process, you can get some sort of a process map. Obviously, I don't expect you to look at the details of this map, but in general, people start at the top pink box and they go to these blue boxes, and then they live in the bottom pink box. This is just good description analytics. Tells me, hey, what is the process? This is essentially the queuing network that I see that is operated, and I can read it from the data. I can also provide you some dashboards of, what is the length of stay, what is the 90th percentile of length of stay, how different customer types have been treated, and so on. So that's just good descriptive analytics. The trick is, however, what is interesting for me pushing the management analytics further, is that if I now have this queuing network structure, and I can understand each one of its building blocks, and I get a good predictive model for everything that happens within each one of these building blocks, I can combine them together and I can create a simulation model of the system. So in this dashboard that you see, again, it's very small. Blue is the descriptive analytics. This is what happens in the data. And orange is what happens from the trained simulation. So basically, to doing the comparative analytics and the predictive analytics, what we need is a good model of the system that captures what's going on in the system well. Here, all I do is predictive analytics. I'm looking at the exact system and I simulate it, right? But because I use the building blocks of queuing theory, different stations, number of servers, routing, priorities, all of these wonderful things, and I learn them well from the system, now, not only I can give you a prediction of what will happen in this system, I have a simulation model that can take you and do the comparative analytics and the what-if analysis. In this example here, the plot is of the number of people in the system, and I speed up one of the stations, right? So it decreased the number of people in the system, essentially. So now you can start doing what-if analysis by playing with your simulation. And that's the comparative analytics. You're starting to look at different systems that didn't exist in the data. But because you have understanding of the causal impact of the queuing structure there, you can push the analysis into the comparative analytics. Once I can do this comparative analytics, I compare different options, how much they cost to implement, what is the benefit they give me, so what is their effectiveness. And cost here is not just, I need to pay another $1,000 for the doctor to come earlier, but also the change management, how do I convince people to change and to support this in the long term. So cost is not just dollars of buying another machine necessarily, training people to use it and so on, and using it effectively. And once you do this analysis, you choose an action. So this is kind of, hey, what would be the best system going forward? The trick is that now when you take this action, your entire data is being generated from a different system. So you can read the new data, and now you can go through the same process again and update your simulation model of the system. Now, if you look at this process, essentially steps 1 to 4, you can think about them as the management analytics guy work. She goes, she takes the data, she creates the simulation model. Then she gives the simulation model for a manager, the clinician team, if you wish, in the context of emergency department. And these people now define the different scenarios they care about and then that they can implement, make the choices and implement them, and then change the data. Obviously, you can also think about these steps 5, 6, 7 as being automated. So a nice example, last time I went to the emergency department, it was after I had a minor ski accident, say that I need both an x-ray and a blood test, right? Where should you send me next? Where should you route me next? So you can think about, oh, I can simulate essentially different paths, or I can train a reinforcement learning model ahead of time that will tell me, oh, given the current situation of the system, you better go to do x-ray first, or you better go to do blood test first. This is being implemented and change how the system works and generated. So the analytics team kind of do 1, 2, 3, 4. The business and OM people, if you wish, do steps 1, 6, 7. Now, what makes it a digital twin is, as I said, this synergy where the model and the system impact each other, right? The trick is that if, 10 years ago, I would go to an emergency department and build a simulation model for them, it's about one person here. And if Guangwen will go to an emergency department and build a simulation for them, yeah, she's better than me. She probably can do it on only 9 months. But we would each have different simulation models. And with 9 months to create another simulation model, you don't have this feedback between the simulation model and the system and the data, right? By the time our model is prepared, the system is already different. What we can do today, and I'll show you in a minute when I'll show you the demo for SimulQ, is we can go and do steps 1 to 4 in seconds, essentially. This allows us to then keep on training our system with new data, changing the model of the system, the simulation model, and see what is the next best step in the future. And this creates this digital twin where the model and reality impact each other essentially, and not standing in isolation from each other. Okay, so I talked a lot. Any questions on this kind of mental model, second mental model I'm sharing with you today?
Hi, Professor Baron. I do have a question
Sure.
regarding the what if analysis. So I see from step 1 to step 4, we can design and construct a good machine learning model or simulation model to predict, right? It's for the prediction analysis, and for 5 is a comparative analysis. But what will be the way to to decide whether this what if analysis accuracy can be guaranteed?
Hello.
And is there any robustness check for that? Because I see the action accuracy or effect.
Роза, hold on. Роза, тебе звонят.
Yeah, it's a great question. So the easy answer is it's better than anything else I know on how to do that. The more full answer is what you hope to be able to do in this context is not a full A/B testing, right? The standard way of doing comparative analytics is doing A/B testing, right? I want to understand the causality of things, right? Here in this system, it's very expensive to do A/B testing, right? You can kill someone, right? So what you want to be able to do is to essentially look at what happens in the data that reflects similar things. So, for example, when I said, "Oh, there's a flat tire," it means that there was, one nurse less in the emergency department that day. And if you can go from one nurse less to one more nurse because you see it in data well, you can also go from even one more nurse and try to get an understanding of this, especially if you understand the queuing impact of things, right? If you just think the impact is linear, you're going to be off. We know that. But if you capture the queuing impact of things, you're going to be on. So one of the ways of kind of gaining trust in the simulation model is to obviously train it, then test it out of sample, but also look at the things that you're raising, Chiawen, where you kind of trying to look and say, oh, let's say that I simulate something that I observed before. Do I get the right impact on items, right? So
Yeah.
the easy thing is, oh, in a day that the doctor didn't show up, they had a flat tire, or the nurse didn't show up because she has a flat tire, I can simulate it and see that my results are aligned with the system. So gaining trust in our models is a very critical thing, right?
Yes.
And you know, there's a standard way of how we do this in a data-driven fashion, right? We train our model, we validate it, we test it, we choose different models, right? So the simulation model here, for example, what happens is that Guangwen's simulation model is being run, my simulation is being run, your simulation is being run, and then you choose the best one of them kind of by how it does out of sample, right? So it's not a single simulation run. This is a more objective choice of a simulation run, right? A very subjective simulation that what we do. But what you're suggesting is a critical point in terms of verifying that you can trust the model and testing it out of sample, essentially, not just out of sample in the predictive, as you said, but also out of sample in the comparative. So the great point. Thank you for raising that.
Okay. Thank you, Professor.
Sure. Any other questions on this, guys? All right, good. So let me try to go. So we changed the data. Obviously, I need to emphasize before I show you the demo of SimulQ, there's a special issue of Service Science that we are editing. The submission deadline is in another week. I got a couple of requests to delay it by a couple of weeks, so I will change it to October 15. I'm going to send an email to everyone about this in the Informs webpage later today, hopefully. But just kind of wanted to let you know, if you have great papers that are related to service engineering, please submit them. We're looking forward to have some great submissions there. So let me stop sharing this screen, see if I can, and I want to share my other screen where I can show you the demo of SimulQ. So 1 second, my mouse here is running around. I need to share with sound, and I want to share this screen, and I want to show you how it works, guys. Okay, so everybody see the map, the process map here? Oh, I see Guangwang is saying yes. So basically, you get this a second after you insert, you uploaded the data into SimulQ. And let me play to you, show you how we do steps 1 to 5 essentially. In this is 3 minutes and 20 seconds essentially of the demo. Hopefully you'll enjoy it.
Once the emergency department data is loaded into SimulQ, the first thing you will see is a process map that describes the typical pathways of patients through the process. For instance, here we see 2 pathways, one that starts with triage, registration, assessment, and finishes with disposition, and another that diverges, and after assessment, a consult is requested and a consult arrives to examine the patient. Those are the typical pathways. We can also go and explore the dashboards for some empirical analysis of the data. In blue, this is the actual data of the emergency room between January 1st, 2021 and January 12th, 2021. So it's almost 2 weeks of data, and we see typical performance measures, the length of stay with the different statistics, the median, the average, the 90th percentile, the time to physician's initial assessment, the boarding time, and we see various histograms. All of this is highly customizable, and hence the user icon here. That means that the user has defined those measures, and as users, we can define various new measures as well.
Okay, so this is descriptive analytics, right? I upload the data, got the process map, got the dashboards, just descriptive analytics so far.
Now, suppose we're not happy with our length of stay of almost 4 hours on average and the 90th percentile being 7.26, and we suspect that the initial assessment and the boarding time are the two activities that take the longest. Going back to the map, we will explore the activity analyzer module, which is our way of intervening and improving the process.
This is
Going into the
bottleneck
activity
analysis.
analyzer, we can rank the different activities based on their contribution to the length of stay. We have additional statistics here, but the main statistic is the contribution. We see that the two bottleneck stations are related to disposition, this is boarding, and the initial assessment. For the disposition, we propose an intervention that actually was proposed by one of our clients. Let's assume that the boarding is deterministic at 30 minutes. The way they think about it is 30 minutes at most. So we set the intervention to be deterministic at 30 minutes for disposition. For assessment, we will speed this activity up by 20%, say by adding more capacity to the doctor station. We save the interventions, and just like magic, we run a simulation of 10 iterations, and we're able to examine the impact of our interventions on the different performance measures. Here, next to the original data, we have the baseline simulation data, which is basically...
This is the predictive analytics, right? I'm just simulated the existing system.
The digital model of the system. In a good fit, the orange and the blue should be in high correspondence, and we see that this is indeed the case. The statistics in the orange and the statistics in the blue match each other. A third button that is going to be enabled is when the simulation finishes its run. Currently, that's what happened. We will turn on the intervene simulation data, basically the behavior of our system under the two interventions that we proposed. And we see here that under the intervention, the length of stay, the 90th percentile goes below 4 hours, where it's used to be more than 7, and the average goes from almost 4 hours to 2 hours. And the same thing is happening to the time to PIA and to the boarding time. This demonstrates the power of SimLQ, loading the data, quickly performing the intervention analysis, and looking at the impact of our interventions, all in a matter of seconds.
All right, so I hope you enjoyed it. Every time I see this, I still feel surprised from what we are able to do. What you've seen, this is real data, this is real time, and we've done that not only on emergency department, but also on contact centers, on manufacturing facilities, on court systems, on walk-in clinics, on the process of order to cash. So essentially all of these wonderful processes that are queuing networks of service system are processes that follow this in very similar structure, where you can get from the data to the process map of the queuing network, and then you can start playing with different interventions on it to do the comparative analytics and support the prescriptive analytics. As you've seen, we are still not completing steps 6 and 7, right? What we are doing now is essentially steps 1 to 5. But the fact that we can do this in seconds, and the fact that we know how to do the next steps, to me, gives a really good vision of how AI is going to impact operations management, which is kind of the mandate that Wang Wen gave me when we talk about this talk about, like, hey, let's see, what is your vision to how we go forward? That's kind of my vision, to being able to support this creation of digital twins. Again, done it in the context of queuing, which is my favorite topic, but other contexts you can think of a similar process as well.
I do see one question from our audience. Alex, do you have a question? Okay. Oh, thank you. Thank you so much, Opher, for giving such a fascinating presentation. It was a clear walkthrough from the descriptive to prescriptive analysis and a great peek into SimulQ. I think you have given me a lot to think about, especially on these 7 steps and how can you nowadays combine or integrate the first 4 or 5 steps together to make it so different from the previous analysis. So Now let's dive into a conversation. For our audience, this is your chance to ask questions, share your perspectives, and explore the ideas further with us and with Opher. I'll probably start off with a few questions, but for all our audience, you're all encouraged to jump in and ask questions anytime you want.
Alex, do you want to ask a questions? Because I see you unmuted yourself.
Oh, did I mute it? Am I muted?
So this is my question. Is this methodology just simply discrete event simulation?
Yeah, what SimulQ runs behind the scenes is a discrete event simulation.
Which package did you use as a discrete event simulation? Because numerous discrete event simulation packages are available. So which one did you use?
Much of our code is written in SymPy.
Oh, it's your own unique package written. So you didn't use a commercial discrete event simulation packages?
No. We write our own. We have our own.
Okay, thank you.
Welcome.
Thank you, Alex, for the question. So maybe let's begin by exploring the big picture. So how do you see the synergy between our classical operations management and this modern AI approaches to shaping the decision making for either supply chain or service processes? Or where do you see the most impactful intersection now or on the horizon in the future?
Yeah. So I think the most impactful one is this synergy between the model and the reality. So the standard definitions of a model that I will always use when I would be teaching my students was that the model is a representation of reality that is independent of reality, right? So I can play with the model to learn things, get the intuition, get the insight, and then go to reality and do what I can. And this was the right way of doing things when you couldn't go quickly enough, I would say, with the analysis of the model back to reality. When decisions were strategic decisions or tactical decisions, you needed to pay you and I, 9 months of salary to build a simulation model, for example, right? This is a $500,000 project. You don't take $1,000 decision based on it, or a $50 decision as, where do we send Opher to X-ray or to blood test first, right? Now, when our models are much quicker and because of data, they represent reality in a much more detailed fashion that we used to do, they can interact with reality and then this combination of things. So traditionally, models were independent of reality, and this is why they were confined to relatively tactical or a strategic decision. Even the operational ones were in terms of policy, not in terms of how you do things in real time. Now we have the ability to have these models that work in real time, can give you a recommendation in real time, you can implement it in real time, and therefore we have this digital twin. That's the first thing. The second thing is that we can have much less stylized models. So again, 15 years ago, when I started talking about simulation, I said, hey, let's not pick up, third, fourth order conditions. We have enough mess over things here, and we don't have enough data to understand how the fourth term conditions impact things. Today, in many places, you have enough data, and you can create a more complex model of reality that captures those effects as well. In this sense, being a little bit on the senior side, I feel younger people have much less issues with trusting black box models than people my age, right? The people are willing to work with the black box model significantly more than before, and that was something that we never felt comfortable with, right? Interpretability was critical for us. I still claim that this is critical now, because you don't want to be asked the question, oh, why did you price it at $5? And you say, oh, the algorithm told me, right? You have to bring your own value. If the algorithm told you and you price it as the algorithm said, I don't need to pay you, right? So there are different gentle things in terms of how the world around us is changing because of psychology, willingness to trust this black box and not asking questions like Chiawen asked earlier, right? And our ability to create more detailed models and our ability to do this in real time. So those three things are critical in my mind.
Yeah, I totally agree. So now I'm thinking when I learn, let's say, inventory theory, right, in the PhD class, so we usually figure out what is the optimal policy, which means it is the best policy, in the long run. Nowadays, if we can have this more dynamic setting and, we can make the decision dynamically, maybe we don't have to follow a simple policy, rather we can give like more complicated things for let's say the AI agent or the algorithm to see what to do the next. Yeah, thank you. I guess from your illustration, the SimulQ stands out for this hybrid queuing machine learning approach, and it's pretty fast. So now I'd like to go back to the origin of the story. So what inspires you to develop this simulation tool? And you probably have been talking about, how unique it is, but I want to still want to dive a little bit, like what unique problem does it solve for business compared to the existing simulation or analytics tools that are available today?
Yeah, great question. Thanks. First of all, SimulQ. Why do we name ourselves SimulQ? So Q at the end, you have a sense, I guess. ML, it's machine learning, which is kind of heavily used in SimulQ, and SI stands for simulation. So the idea is, create these simulations for queuing systems. As I said, a more detailed model that I don't have a closed form analysis expression for, right? Those queuing models, those queuing networks are really hard to analyzing closed forms. You have to do approximations or stuff like that. So as I said, today we can get a more detailed model and can analyze a more complex model, not mathematically, but numerically. And why did we start thinking about this really? Arik, Dimitri, and I, we wanted to do some research work together. It started with Arik and I sitting in front of a whiteboard and saying, "Hey, what do you know to do? What do I know to do? Let's see how we combine these things together." And we sit on the whiteboard and say, "Hey, you can do this, we can do this, we can do that." Then we ask ourselves, "Hey, can we do the comparative analytics and not just the predictive, the descriptive and predictive one?" And the key observation that helped us was that once you have this queuing structure, you have the process that generated the data, essentially, you can create the same process. And because we know queuing, much of the causality of the process we can capture. In the context of managing queuing systems, we now have the ability to go really from descriptive to comparative. And doing prescriptive after that is obviously the next step. And again, we have a sense of how to do it. And we say, oh, this is really nice, but this is not only a research project. This is essentially something that has a lot of value in industry. So that goes to the next part of your question, kind of how this is going to be used in practice, what kind of decisions are being supported by this. So we have a few customers now, a couple of emergency departments and a couple of other industries. In the emergency department settings, one of the things that we've seen is really changes of routing of patients. So in many emergency departments, there is a rapid assessment zone or a non-rapid assessment zone, ambulatory, non-ambulatory, or lying and walking patients, essentially areas. And one of the things that we've seen is in this specific hospital we work with that they are underutilizing these rapid assessments. So there are many patients that can go there medically, right? I'm not a medical doctor, but many patients that can go there medically, but are not going there, and they basically block the non-rapid assessment or the main zone of the hospital. So hey, how about you change this? So they moved from, 1/3 of people going to the rapid assessment zone to 40% of people going to the rapid assessment zone. So this is really nice. We could then, this is essentially an A/B testing for us, if you think, going back to the question we had. And we could see that when we simulate this and what happens in reality are close to each other. That's one thing. The other thing that we've seen is really interesting and not going to surprise the people in this crowd is that once it has been done, the performance became a little bit better, cut about half an hour of the length of stay, of the average length of stay, which was really nice. The trick is that after about a month or maybe 2 months, the ambulance dispatchers noticed that this hospital is more effective. So more ambulances started going there. After another month or so, family physicians in the surrounding also found that this hospital is a little faster. So they started sending more patients there. You go to your doctor, you need an MRI, they can tell you, oh, lineup is about half a year, or, go to the hospital, you're going to do it today. Right? So what happens is that performance improved, then demand started increasing, strategic customer behavior, right? That's what is kind of much of the work we're doing, how people are responding. The strategic customer behavior, ambulance drivers, patients, doctors, increasing demand, moved the length of stay to about where it was before, essentially, which is the equilibrium in this region, but increased demand by 5% in a year. Right? So those are the kind of changes that happens, and you can support with an analysis like this, which again emphasize the need to understand the causality of things and how things respond.
I see. So when you implement them, do they always follow the what you suggested in the simulation, or they sometimes could be deviate from them?
No. So that's kind of it's human nature on many things. So when I come to you and I tell you, hey, your students don't know the material at the end of your course, you're going to tell me, look, the students didn't have the background. Look, there was a holiday in the middle, so I missed a class. Look, the TA didn't do the work well. We're not going to blame ourselves typically. So in many cases, I go to this emergency department, and what they tell me is, look, the consult time is very long. Why do they tell me the consult time is very long? A, because it's true, and B, because they don't control it. The consult time is someone coming from the ward to the emergency department. It's not a doctor that works at the emergency department. So this is someone else's problem to some extent that imposes issues on me. So now they say, oh, let's see what happens if I cut the consult time to 2 hours rather than 8 hours. So wonderful. It's a great scenario to run. But if I don't control it, there's nothing to implement here. Right? So, part of the change management, there are discussions with clinical teams is we sometimes run some scenarios that are not realistic, but trying to convince them to do more things. And again, it's not everything that is easy to do in the simulation is easy to do in practice. For example, if your nurse are unionized, changing their shift of nurses can be really effective, but may not be easy to implement in the short run. Right? So there's a lot of things when you go into change management and changing things, many missing parts. The trick is that the way I see it, the process of this digital twin and the process of modeling in general should support this change, right? If I go to you and I tell you, hey, if you answer students' emails, it will help them to understand the material significantly better. He said, okay, I don't like answering students' emails because it takes a lot of time and it's one-on-one, and I'm here to teach a big class, but if it helps, let me do it, right? We're basically good people. We want to deliver health well, we want to deliver teaching well, But sometimes you need a little bit of understanding of what are your suboptimal decisions create and how better ones would improve things in order to convince people to move and change. It's not always sufficient, but to me, it's an important tool of convincing people to change how they work.
Wonderful. Thank you for sharing your insights. So looking ahead, I and probably I think believe many of our OM scholars believe that the operations management could accelerating the technology integration across in different sectors. So I wonder, how do you envision the future of autonomous vehicles, or telemedicine or smart manufacturing, that hopefully integrating operations AI for the real-time decision automation?
Yeah, good question. So again, if you think about autonomous vehicles, the ultimate black box model that I need to trust, right? I mean, it's really a matter of life or death, right? This is driving, being on the road is probably the most dangerous thing that we do daily in our modern lives. So that's, I think, one of the reasons why AV's adoption is significantly lower than what people predicted it would be. I mean, when I started working on autonomous vehicles, the predictions was that by 2025, the vast majority of new vehicles are going to be AVs. That's clearly not the current situation. There's going to be a little bit more time. There are a lot of dangers here, and this is one area where interpretability of AI is really critical. So you see the vehicle in front of you slowing down. Understanding why do they slow down is critical. If they slow down because they want to turn to the right, maybe you can pass them. If they slow down because there's no place to go, you need to stop. So there is kind of understanding why they did something, why their AI took a decision is critical for the next AI to take a decision as well. So that, to me, adoption of these black box models is something that, as I said earlier, maybe younger people have more trust in those systems than older ones. I certainly feel my kids trust my car more than I trust it. So this their adoption is different. Going back to where operations management can impact this, I think is both by creating better algorithms, also in the context of interpretability. Again, I still see a manager taking decisions and not kind of everything being done autonomously. I think there's a big societal question here. If you look at the Industrial Revolution, its claim to fame was that it takes hard jobs and does them with machines. So when things are heavy, when things are hard to do, and people would have to work really hard for this, you replace it by a machine that does it better. I think what AI brings to the table is a similar thing, but for hard mental things. So in terms of creating, possibly less high-paying jobs and increasing the gap between the rich and the poor, certainly something that I am concerned about. I'm not sure how OM people can help with that, but to think about how to make sure we are not cutting the branch we sit upon to some extent. Yeah.
I see. Yeah. Coming back to the simulation or the 7 process that you described in the talk, right? I'm just thinking, so let's say for the autonomous vehicles or this on-demand, vehicle routing, sometimes they are more complicated than, simple queue because there are location problems. So which means maybe sometimes there's a lot of independent properties does not satisfy. In that case, so the simulation probably takes longer time. And then the question I'm thinking would be, so how do you decompose the 7-step of process, right? Which step should do like upfront, or which steps should do like dynamically? Would that be, the way to integrate, the digital twins to those type of like more complicated settings?
Yeah. No, it's a good question. So some approach of doing this is going through sort of these foundational models where essentially I have a good model for a robust model for some application, and then I tailor it to your application. In the context of class teaching, you can think, sitting in your class and several of the other great professors that we have, and see how they deliver a class, and then create a training program for others that is based upon that. In the context of simulation models, for AV, much of what is going on is, you have some AVs driving on the road, you see when they do well, when they don't do well, there's some sort of reinforcement learning there. In the context of emergency department, you can think about my simulation of SimulQ. I know how to simulate emergency department. I've seen, 10, 15 data sets of this. I have a very solid model. I know how to train my model well. Now you give me your emergency department, and I can easily create a model that would be solved faster because the underlying model is there. But still, computation time, which we as research often take for granted, is becoming very expensive and very, very demanding in the context of modern AI.
Mm-hmm. Yep, thank you. Thank you, Opher. I do see one question from our audience, Qiaowen. Qiaowen, I have unmuted you, so feel free
Okay.
to.
So I can see the two distinct advantage for simulation model. One, it can save a lot of money. And second, it has a great interpretability power. But my question will be, how would other intervention, like new intervention, like the AI, for example, the AI agent adoption for collaborating with a doctor or consultant in the whole system would damage the interpretability power? Because sometimes I can see it has some very nuanced behavioral response to, for example, how the doctor or patient or consultant react to the AI adoption. And will the system, the simulation model system, can capture that kind of like nuanced behavioral response? And how does that influence the whole interpretive power and accuracy and so on? And how do you like interpret this new integration effects of that to your business partner?
Yeah. No, I think it's a good question. And I don't think we have a magic solution for this. I want to emphasize one important part that your question made me think about. In many cases, people see AI as helping them to do the current processes. So I call this a point solution. Let's automate something. Let's do that. If you don't change the process, you use AI just to support your current process, it's can certainly be helpful, but that's a point solution. What we want to be able to do in many cases is to change the process in which we operate, to use what AI enables us to do in order to change the process. So if you think about telemedicine, for example, right? The standard way of doing business is, you go to your dermatologist, say, and you get an appointment with them. May take 2 months, 6 months, depending on where you are in the world. And one can say, you can also go to a telemedicine. So that's kind of adding another channel of service. And why it is not there, it's because, strangely enough, those channels are more expensive than going to the family doctor, because there is a family doctor or a dermatologist, excuse me. There is a dermatologist that sits there, but they need to work kind of an overtime and with extra technology, so it's more expensive. Maybe price will go down. It should go down, but for now it is higher. I claim that a more intelligent solution that's just adding another capability of telemedicine using the AI, which is already changing the process, is to also only use it when the in-house dermatology is very busy, right? So basically, if the in-house dermatologist sits there and do nothing, I don't want to send you to the AI solution, to the telemedicine solution, right? I want to send you to the in-house doctor. Only if there are enough people in the system, optimize this threshold, if you wish, you want to send them to the telemedicine. And my take is that's the idea of being able to use AI when you need it, when it is more effective, to save on the resources, to save on the costs, and to manage things better. So that's not, oh, let's just change implement the current model and allow the current doctor to get a picture of your skin condition before you came to the office. That would be a point solution of using AI. It will speed up the current doctor's work. But if you use it the way I described it, by kind of sending people there in the right time when congestion is high, this is a more complete solution that changes how we work with things. And I think we need those systematic solutions rather than these point solutions. Sometimes, as Guangwen suggested earlier, they are harder to implement, but this is where we need to go in using technology better, essentially.
Okay, so it's kind of like give a very high level adoption for AI, like how to integrate that in the system, especially for some demand shock, right? So yeah.
Yeah,
Okay,
you want to take advantage of it to do things that you couldn't do before, essentially, not
okay.
do the same things that you've done. Right? It's okay to improve the same things that you've done. And cut the time it takes you to fill a form. Wonderful. But maybe you don't need the form.
Yes, yes. Thank you, Professor.
Thank you, Opher. Before we close, I do have one last important question to ask. So many of our OM scholars also aspire to convert advanced academic theory into practical, business-ready, AI-driven solutions. So what advice would you offer for, bridging this gap, especially for those seeking to optimize the real service and supply chain environments?
Oh, that's a tough question. The way I see it, the most critical part is to get support from a great team. I think, especially in our academic life, we tend to focus on something specific and we become expert in this specific thing. Sometimes it's hard for us to understand other things as well. So get a great team of people behind you that will help you to understand other things. Being an entrepreneur, raising money out of VCs is a very different position than teaching and doing research, essentially. Not something that I would know how to do. So I'm glad I have a lot of support in this sense.
Yeah, thank you. Thank you so much. So I think we have 1 more minute. We do have time to open up the floor for 1 or 2 questions at most.
Thank you guys so much for coming. Thanks for the question, guys. It's good seeing you. Hope I'll see many of you at Informs.
Yeah, thank you so much, Opher, for these thoughtful insights sharing with us today. And thank you for everyone participating, and I hope everyone enjoy the rest of your day. Okay.
Thank you, Guangwen, for organizing this. Have a good one, guys. And Happy New Year for all of you who celebrate the Jewish New Year. Shana Tova.
Yeah, Happy New Year. Bye.
Bye-bye.